Hello and welcome to Technical Utkranti, and today we are going to see n queen's problem. This is the seventh question in the recursion and eighth video overall in the recursion. Alright, so these are the videos that we have released till now in recursion, and here is the question. So you're given a chessboard of size n cross n and n queens. In how many ways can you place n queens in an n cross n chessboard such that none of them can kill each other? We need to find all such configurations. For example, for n equal to 4, one configuration is this and another configuration is this. So as you can see, this queen can only kill this way, or this way. But there are no queens placed here. This queen, no queen placed here, no queen placed here, no queen here, and no queen here. Similarly for these two queens, and same is for this configuration. Now, how can we think about solving such a problem? So, before diving into code, think about the algorithm, how it is going, how the approach is going to be. So, this is the 4x4 chessboard. I know that a queen can kill in a row, in a column, in a row, and in diagonals. So, I know that one queen can come in one column, that is for sure, right? And then there are three other checks, which is no other queen is in that row, no other queen is in that upper left diagonal, and no queen is in the lower diagonal, right? Upper diagonal and lower diagonal. All right. So if we proceed column by column, right, and try to place a queen in a particular cell and then hop on to the next column, then we can think of finding a configuration. For example, we have seen in the previous slide this, 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 and this is, sorry, and this is one valid configuration. Now, how can we go about doing it? This is the first question. And the second question is, once I have identified a valid configuration, there could be more valid configurations. So as in that particular slide, we saw that other valid configuration was this, this, and this. So once I have found this, how can I find this also? So this happens through recursion and backtracking. All right, so more of it during the code go through. All right, but firstly, we'll see how can I find the first valid configuration. As we start from the first column, we know that no queen is placed on the right as of now. So for any particular column, to its right, there is no check to be done. All the checks needs to be done for the left part. All right. So for the first cell, I have nothing to the left. So I can just simply place a queen here and hop on to the next column. Now for this column, we have something on the left. So we need to check that for any particular row, comma column, there should be no queen in that row, right? Secondly, no queen in the upper left diagonal. upper left diagonal. And third, no queen in the lower right diagonal, means this one. So if I check this particular cell, then I find that in that row there is already a queen. So this is not a valid thing. If I come here, then in that row there is no queen, but in the upper left diagonal there is a queen. So this is also not valid. If I come here, then I see that in that row there is no queen, upper left diagonal no queen, lower left diagonal, not lower right diagonal, lower left diagonal, there is no queen. So here I can place a queen and hop on to the next column. Over here, I cannot place because in the same row there is a queen. Here I cannot place because lower left diagonal there is already a queen. Here I cannot place because in the same row there is a queen. And here also I cannot place because in upper left diagonal there is a queen. So once I see that in a particular column there is no possibility of placing a queen, then I need to backtrack. So this would basically mean that I cannot have the queen placed in the previous column the way it is placed. So this is gone. And I place a queen over here. Now I again hop onto the next column. This is not a valid position. What about this? Yes. In same row there is no queen. Here there is no queen and here there is no queen. Alright. Then I hop on to the next column. I cannot place here. I cannot place here. I cannot place here because of this diagonal, and I cannot place here because of this row. So again, this means that the queen placed in the previous column was not right. So I cannot place a queen here. Can I place a queen here? No, because of this queen, and not here because of this queen. Which means that queen here is not at the right position. So I'll backtrack. So again, I'll backtrack because all crosses over here suggest that I cannot place a queen here. So I place a queen here. Then I hop on to the next column. I cannot place a queen here, not here, not here. Here I can place. Then can I place a queen here? No problem in the row, no problem in the lower left diagonal. And there is no upper left diagonal. So I can place a queen here. And then I hop on to the next, this thing. And here I cannot place, here I cannot place, here. This is fine, this is fine, this is fine. So here I can place. So I have one solution with me. Alright. So this is the first solution that we obtained. Now what will happen is it will backtrack. So whatever is placed there will go away, and different values of the board would be tried. So this is not valid. This is not valid. This here it cannot come. So Q cannot come over here, and Q cannot come over here. So Q, it will try over here, right? And then here it can come. Then it will come over here and then over here. So we'll get a second solution, but that is solely because of recursion and backtracking. How it is implemented, we'll see in the code. We'll have column and some other inputs as well. And for the first recursion, the value of column will be 0. Then we'll run a for loop. Right. Then we'll run a for loop for row in range of 0 to n minus 1. In this way, in one recursion call, I'll traverse through all the rows of a particular column. Then I will see is valid row comma column. So is valid will check all these three conditions. If it returns true, then we can place a queen at that. So board of row comma column is equal to q. All right. And then the recursion call will happen for the next column, column plus 1, and other inputs. Let me make this matrix of 4 cross 4 again. All right. So if we are in a particular row, we just need to check if in that particular row is there queue placed previously. All right. So I will create an array of size n. So I can say, and I create an array of name left row of size n and place four zeros in it. Right. Now, if I place a queue in a particular cell, then that particular row value, I'll set that index to 1. So if I place a queue here, then I will make this one as 1, the first index as 1. Now, for any subsequent cell in that particular row, will have the same value of r. So I will use the same value of row or r and see if left row of r is equal to 1, then we have to return false. Correct? All right. Now, there is similar hashing check for the upper left diagonal and the lower left diagonal. So, if I sum up for each cell, the left and the row and the column values, what I'll get. So, I see that for the elements lying in the same uh, lower left row, right, the values of left row plus column would be the same. So, I create an array of size 2 into n and fill it with zeros. All right. So this is index 0 and this is index 7 or 2n minus 1. Now, if I place q over here, let's say, then I will take the row and column, add it up, and set the corresponding index to 1. All right. Now, if I check for this particular element, what is the value of row plus column here? It is 2. And 2 of this particular array is already 1. So in that case, we return false. I hope it makes sense. Similarly, for left up, I'll create a similar array of size 2n. Right? Let me draw the matrix for it again. So as you can see here that the values of the upper left diagonal or upper diagonal is same, right? So if in this array I am filling this particular element, so I will set index 3 to 1. And then when I come, let's say here, and again I calculate n plus c minus r, which is 3, and I see that, okay, left up of 3 is 1, then I need to return false. I hope it is making sense, right? So let's quickly jump to the code and finally understand it. So this is my answer list or array. This is the board. Left row, which I have just showed you for the three checks, up diag and the lower diagonal. All right. Okay. Now I is in the range of n, and I create a board of dots. Right. All right. So this board would look like dot 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 dots of rows. All right. Now to begin with, I start with zeroth column. I give the board the size, which is, for example, 4. Answer, left row. These are the three checks basically. All right. So here onward starts my first recursion. This is the base condition. Let's not look at it for now. Now for column 0, I pass through all the rows and I do these checks. Left row up diagonal and the lower diagonal. All right. If so, here I've used n minus 1, but in the explanation I was using n, but n minus 1 is also fine. That's why we are having the size also 1 less. Okay. So if these checks are satisfied, I place queen in the board and I set these particular entries in the hashing arrays equal to 1, and I hop on to the next column. All right. Now for column equal to 1, again these checks would be done, and then column 3 will happen. Now, if column is equal to n, all right, then we will add the code to the answer. All right. Now, while returning back, so this is called backtracking. While returning back, we need to reset the values of these hashing arrays to 0 and the value of that particular cell in the board to dot. Because when we backtrack, we reset everything that we had set while going forward in the recursion call, right? So that is how we would be able to check all the configurations. All right. So let's quickly submit it and see if we can have our answer. Yes. So I hope you understood the question, the solution, and Python code of it. If you did, please give it a thumbs up and subscribe to my channel. Thank you. Bye bye.